Hi, folks. This is Mr. Messerman with the Forces of the Universe podcast. Forces of the Universe number 13. I can explain the relationship of mass and distance in relation to gravitational force. Well, let's have a little history here. It started with Tycho Brahe, who carefully recorded data on all the planets and their positions in the sky. Ironically, he, to his death, thought that the Earth was the center of the solar system or the universe. Johannes Kepler analyzed Tycho's data. He graphed it and he figured out what was going on with the planets. He figured out the relationships between their distance from the sun and how fast they move. Sir Isaac Newton explained the data. He came up with a plausible explanation that we call Newton's law of gravity. And here it is, Newton's universal law of gravitation. It can be stated as the force of gravity equals a gravitational constant times one mass times a second mass divided by the distance squared. G is the gravitational constant. We have the mass of object number 1, the mass of object number 2, and the distance between them. Now G equals 6.7 times 10 to the minus 11th Newton meter squared per kilogram squared. And it was determined first by Henry Cavendish.
Okay, go.
These two bouncy balls here are pulling each other together by gravity. Okay? Why don't they move? If they're attracting each other, why don't they roll together? Any ideas? Come on, somebody speak up. You don't have to be on camera. Okay, that is true. They're about the same mass, so they're pulling with, the force is equal. By the way, like I said, it's equal for you and the Earth, right? So you pull the Earth up with the same exact force that it pulls you down. So that's a good question. Why doesn't the Earth come up to greet you? We always go down to meet the Earth. Why doesn't the Earth come up to meet us? Because it's so heavy, exactly. And because Newton's law, F equals ma, the mass of the Earth is so great that the A is going to be microscopic. It doesn't really, you don't really pull the Earth up. You're still pulling on it, though, with the same amount of gravitational force. But it's so big that the force acts on you because you're so small. And you fall down, right? What's holding these in one place? Here. The table. The friction. The gravity pulling down on the Earth is so much greater than the gravity of these pulling together that they're just going to sit there. What Cavendish did is he put these up on a balance so they were free to swing, and he saw them move. And he put different masses together and figured out how much force things make, depending on their mass. He changed the weight of the balls and everything. And he came up with G, the gravitational constant. All right? Does that make any sense at all? Clear as mud?
So here's the problem. The force between the two balls is 6.7 times 10 to the minus 11th Newton meter squared per kilogram squared times 0.034 kilograms for one ball and 0.032 kilograms for the other ball. And we put them 30 centimeters apart. And when you work that out, plug it into your calculator, you get an incredibly tiny number. 8.1 times 10 to the minus 13th newtons. It's very tiny. Thanks for watching.